Okay, so let me start page 99 here. We this part, the concept is not so difficult. So we have a traction acting on the same area of V2 with normal. Minus n is this. Okay, all the possible surface passing through X. We distinguish three passing through X. Where is X? Anyway, all possible surfaces passing through X, we distinguish three coordinates plane with normals. EI and denote tractions on these plane by sigma and surface moments by mi, sigma I, mi. Three coordinates. So not so clear. Three coordinate planes with normals. Yeah, normals EI. Okay. So I goes 1, 2, 3. Right. So if you have X, so you can put you can put any surface like this, which include X. Then you can specify this plane by this way, N. Is that right? I'm not sure. I'm not pretty sure. So there is only one plane, and I think what we can specify is normal. Normal, right? Like normal. Then you can say this normal vector is n1 e1 plus n2 e2 plus n3 e3, right? This is okay. But now it says EI itself is a normal. But anyway, so I don't know. You can change I to n to I. Now n is changed to I for some reason. And the surface moments by mi. Moment, the concept of moment is not clear much here, unfortunately. But I think we have to move on to relate the traction. Let me see. To remove. Let me see. Let me pick something. To relate a traction vector on the coordinate plane passing through X, the traction vector sigma n acting on arbitrary plane with normal n Yeah, we construct an infinitesimal tetrahedron as shown in figure 8.2 with an inclined plane with normal n. Having an area delta A, the areas delta AI that are the projections on the area delta A along the axis xi and are related to delta A in the form. Okay, I think it is okay. Denoting the volume of the tetrahedron by delta V, we may balance the linear momentum of the tetrahedron. Linear momentum. What do you mean by linear momentum? Linear momentum of tetrahedron. As this, where the velocity V, body force intensity, and the traction have to be interpreted as mean value within the volume and respective area. It is a little bit complicated. What is F? What is F here? What is this F? The velocity V, body force intensity, and all the traction has to be interpreted as mean value. And what is delta V? This is the volume. Maybe okay. I think this one, F is missing here. Body force intensity F. When we divide this equation by delta A and let delta A go to 0, the term containing delta V being a higher order in delta A go to 0. The mean values become corresponding value at the point x, and we get this way. Sigma of n is sigma I ni. Okay. This result establishes the importance of the tractions on the three coordinate planes. Given the normal n of any plane, the traction sigma n can be found in terms of the tractions sigma I. Through the construction of a similar tetrahedron using the balance of angular momentum, we can establish the surface moment relation, something like this. In this process, we have to assume the angular momentum of the tetrahedron. Net body angular momentum, we have to assume the angular momentum of the tetrahedron. Net body moment and the moments that are due to the body forces and surface tractions are of a higher order in this is not so sure. Okay, net body moment. Of course, this is a higher order. And the moment that are due to body forces, this is higher order. And what is surface traction? Surface traction, is it higher order in A? Surface traction. The moment by surface of traction. It's not so clear. Not so clear. I'm sorry, I don't understand this. Cauchy stress and couple stress tensors. The traction vectors on the coordinate planes can be presented in terms of their component as traction vectors. Okay, where sigma ij are the components of second rank tensor called the Cauchy stress tensor. The first index I represents the coordinate plane in terms of normals, and the second index J represents the direction of the component. J, interesting. Okay. The component sigma 1, 1, 2, 2, 3, 3 are called the normal stresses, and the remaining 6 off-diagonal components are called shear stress. Component sigma 1, 1, sigma 2, 2, and sigma 3, 3 are called the normal stresses, and the remaining 6 off-diagonal components are called shear stresses. See, I think I can explain physically here. This picture is, I think, is good in some sense. So we can have, I think, sigma. There's an area. I think sigma. You have some area A. Area. This is called area 2. Area 1, area 3, right? So, and what I think is A sigma n equal A1 sigma 1 plus A2 sigma 2 plus A3 sigma 3. This is force balance. The force are balanced, right? Then what is the sigma 1? Sigma 1 is actually like this. Sigma 1 E1. So sigma 1 is not, I can say sigma 1, this is vector, this is not parallel to E1. See, N, this is normal vector. This, okay. So if you have plane like this, there is a normal vector. This is normal vector, but sigma force is different. So this is like force. force on each plane. Yeah. So then you can say sigma 1 is sigma 1, 1, 1, 1, 1 plus sigma 1 to E2 plus sigma 1, 3 E3. Right? And sigma 2 is sigma 2, 1 E1 plus sigma 2 to E2 plus sigma 2, 3 E3. And sigma 3 is more like sigma 3, 1 E, sorry, sigma 3, 1 E1 plus sigma 3, 2 E2 plus sigma 3, 3 E3. Yeah, this way, right? And this sigma n is a little bit strange. So how do you write sigma n? Sigma n you write, I'm not so sure about this n. Is this correct? Let me work out. I don't know. Let me try to work out whether this is correct. I have some question mark. So, and for n case, I think we have this equality to an I. We call this I equal a1 e1 plus a2 e2 plus a3 e3. Okay. Then we also have the other one, a sigma I. This is a1 sigma 1 plus a2 sigma 2 plus a3 sigma 3. Yeah, so then can we obtain one from the other? Can we obtain one from the other? And this I, see, I think, I think I have a mistake. This is n. This is like n. See, this n is vector. So then this is n. Yeah. And this is more like, okay, sorry, confusion. I think this is more like N1. This is N1, N2, N3, right? So then we can divide A. So this is like A, 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 right? It's a little bit confusing. Why? It's a little confusing. I'm not sure. This is N, sigma N, sigma 3. So then there is a sigma I, E. E is used. Ni, delta A. Okay, so this is Ni. Yeah, you can see here. So this Ni is actually A, AI. Because I set A equal delta A, AI equal delta AI. Okay, so in this case, so this is a force balance. From this exact force balance, no, you delete this, then this one become N1, this one become N2, this one become N3, right? Yeah. So this is same. What I write here, this is exactly same. This thing is same as this. Yeah. So then we have Cauchy stress tensor, something like this. Then we have transformation of the stress tensor. In equation 8.8, we may keep the plane fixed, maintaining the traction on it while a new coordinate system x prime is introduced. Sigma n is sigma I n I. Right? We may keep the plane fixed, maintaining the traction on it while a new coordinate system x prime is introduced. Where is x prime? Where is x prime? I'd say this is x prime. This is x prime. And denoting the stress and components of the normal n by sigma ij prime and ni prime respectively. In the new system, we get sigma n is, how do you call it? How do you no picture? No picture about this. I think the attraction of while a new coordinate system is introduced, denoting the stresses and components of the normal n. See, we have like some plane, so we had something like this. So then we can set another coordinate like this. So then this is same plane. So this is like x prime, y prime, z prime, x, y, sorry, x, y, z, probably. I'm not very sure. I'm not very sure about this. Maybe, okay, I think we should combine this and this. This and this. Maybe. So you have sigma. This is more like sigma, sorry, sigma I, sigma prime I, and this is vector. Yeah, so you can see this then n1 prime. So you see the same structure as this, right? So this one using prime coordinate you can express like this. Then using the original coordinate you can express like this. And this is same thing. Okay. We can establish the transformation law for the stress component as that for the second rank tensor, namely sigma ij prime is qil qjk sigma lk. Yes. A similar representation holds for the surface moment, where Mij are the components of the coupled stress tensor. The coupled stress tensor is known as the Koserat stress tensor in honor of the pioneering work on moment stresses carried out by the Koserat brothers in the early 19th century. The transformation law for Mij can be obtained to be that for second rank tensor, as we have done previously. Mij. Okay, I think let me skip the moment part. Maybe moment part we skip. The principal stress is on an arbitrary plane with normal n. The fraction sigma n can be obtained as sigma of n equal sigma ij and j ej. We may resolve this with one component perpendicular to the plane and remainder tangential to the plane. Denoting the perpendicular component by n, we have n equals n dot. Okay, let me see how many pages do we have? Shear stresses. Oh my god. Okay, so let me take a break here a little bit. Then we can make another video. Okay, so see you.